Okay, this is fine. So now I am interested to see how many people are interested in what activity. So how many people are interested in making like hackathon for graphics and sensors and microphone and so on the kind of FPGA board. So how many? Okay, so how many people are interested in interview style exercises and simulation? Okay, so you can actually do both, but before we start lecture from like other presenters who will talk about like ASIC design, let's spend next 40 minutes making sure that everybody can run with FPGA boards and with the simulation. So and once you know how to run it, then we will listen to this presentation. And so I like already sent everybody a link to a post. So if you go to Verilog Meetup, if you go to Verilog Meetup website, so you can see this post moving your design. Oh, and how many wants to like experiment with a new board? So like other such people. Okay, so you want to experience with a different FPGA board. Okay, so I need to explain the infrastructure, how to do this. And then like if you want to make a support for a new board, I have large collection of boards which I will put tomorrow. And so you can see like other boards. Also, like I heard that you are here in like of Kalpoli wants to use microchip like FPGA boards in your classes, which are like former microsemi, former Actel. So I actually met with person from microchip on one of exhibitions. And he showed me a type of board you probably plan to use. So you can figure out how to put this infrastructure compatible with those boards as well. Because kind of idea that you run examples on different boards and you can just like switch the boards. Yeah, so for this reason, I will talk tomorrow about this board infrastructure. Yeah. Also, we are getting tomorrow a student from UC Santa Barbara who will make a presentation about this like AI challenges, which also relevant to the like interviews, like student interviews. So what happened is that so like every year. So we like at Samsung, we like interview interns. So we have like interns who go to like a foundry in Texas, and there are interns who go to like our group in San Jose, and we do like interviews for those interns with like various questions. Like I have my questions, like other interviewers have like other questions, but also there are some people who write me to LinkedIn asking for internal referral, because I can make referral to the like internal database, and this sort of improves chances. So this year, like 30 people ask, like more than 30 people asked for this referral, and they decided like last Christmas to somehow filter them, because I don't want to spam my like our like management with too many resumes. So I need to somehow like filter them. And what they found, and they gave them certain task. This task is about pipelining, similar to what we discussed before the lunch. So, but what happened with this task? Yeah, so I wrote how to fail students who rely on chat GPT. So like, yeah, so this is like my like experience with, so because this was like online, many students started to use LLMs to generate the solution. The problem is that LLMs in Christmas were not able to solve my task, my like challenge. And because they were not solve my challenge, I suddenly realized that the very same thing can be used by AI companies for testing to whatever they produce. As a result, I had some long conversation with person who is like silicon strategist in one of like top companies in this like new AI area. So they were using this particular challenge, and also with startups, with startup from Berkeley and startup from Stanford, and then this challenge was actually solved in August by new versions of LLMs, but then they created another challenge, which they solved only in September. Now we are preparing third challenge, and this student from UC Santa Barbara is going to talk about it. And this challenge is also in my like interview questions, because you see, like LLM is not good in solving pipelining and like credit-based flow control tasks. So this is something which schools don't teach, but everybody uses in industry. But let's, yeah, with this challenge, I will probably talk more tomorrow, but this challenge is very similar to what we discussed before the lunch, except it uses blocks from a real CPU called the Valley. So let me show you. Yeah. So here is the like essence of this. Here is the essence of this challenge. Yeah. So kind of to do this challenge, I explored idea of like Mad Max movie. So if you see this Mad Max movie, those guys are building like cars from pieces of other cars, right? So basically, I got a CPU created by like some professors and like other people in Harvey Mudd College. So this CPU is called Wally. So let me show you what the CPU is. So if you go to GitHub, GitHub Open Hardware, GitHub Open, yeah, it's this one. Yeah, so there is some open source CPU called the Wally. Yeah, so this is also pipelined CPU with 5 stages, just like what you learned in your computer architecture class, right? But this CPU has a floating point unit. And this CPU also has a MMU block, which is a memory management unit. So who knows why this is important? So have you studied like virtual virtual addressing, like TLB, so the cause stuff. So the thing is that TLB based MMU is critical if you want to run Linux on this processor, because without TLB Linux doesn't run. So their CPU is also written in Verilog, just like simple student CPUs, but it can actually run Linux. And they are putting some book which was supposed to be published like New Year, but it's now delayed. So this is RISC-V system on chip design. So this expected is March 13. Oh, 2026. This was expected release of March 2025. Now it's 2026. Like anyway, which is like great because AI doesn't read this book, you know. And because of it, AI cannot solve the problems related to this book. So now what I actually did, I got a CPU, I got FPU blocks from this book. So you go to source, you go to FPU. So like I got the all like implementation of the floating point multiplication, addition, and so on. And then like together with other people who help with this example, we put it in a series of wrappers. And for like multiplication for subtraction. And we just asked to compute formulas similar to formulas we talked about before. And but instead of like abstract devices, we use actually blocks from a real CPU to compute like discriminants of quadratic equation, and like so like I gave like each of 30 students individual formula, and some of them were trying to use LLMs, and like LLMs did very badly on it. So like LLMs, first of all, LLM cannot figure out at that moment, couldn't figure out. Now like LLMs can do it. Couldn't figure out the latency of each pipeline blocks. So because they like didn't know whether something takes like 1 clock cycle, 2, 3, 4 or more, like LLM was writing something. For the illustration, assume latency is equal 1, just because LLM cannot analyze Verilog well. But the problem is that if you do this, then constructed block will not pass my test bench. Then some students were trying to make LLM to make also test bench for them. So use my test bench for checking. And we're creating their own blocks and so on. So, so this is actually a very convenient example because it tests that person can work with somebody else's sub blocks and with somebody else's test bench. So, but some like the students who actually didn't rely on like LLM, were thinking by themselves, they actually did it well. Yeah. So if you are trained with such exercises, then you can do well with or without LLM. So like yeah. Then think what LLM was not able to solve even after August. So here is a illustration for thing called credit-based flow control. It's a mechanism which is heavily used in industry, so like everywhere. So like Apple, Samsung, Juniper, like AMD, and so on. But it's not in textbooks except for a recent textbook by David Greaves in Cambridge, but they don't have examples in Verilog, and we have examples in Verilog. So basically, suppose that you need to build a block which computes formula, but this block has extra signal called ready, telling that this block cannot accept new data. So like you have like chain of block, one block is sending request to compute something to like another block, but suppose that block on the right cannot accept a result, and they need to signal that it cannot accept something. So basically, in order to make things not to be broken, we need to put FIFO after this pipeline and put some logic around that makes sure that whatever goes through pipeline will be drained into FIFO and sit there until another block requested. So, and there is a whole bunch of interview questions about this, asked everywhere. The most fancy question, was invented in Apple, but like I will not like, tell because this like combines the thing with the clock main crossing with credit-based flow control. But we will go tomorrow through such exercises if you have time. This is just like preview for tomorrow what this student from UC Santa Barbara will talk about. Yeah, so because actually I want help in construction of more such questions. So, but now let's go back to let's go back to what we need for to run simulation. So let me show a simulation example, and then we'll try to install things on your computer. So for simulation example, what you do is so you can get special repository called system Verilog homework. So this is also the GitHub repository system Verilog homework. Then what you do is this has like questions you do in simulation. And this starts from a very simple questions. So this starts with questions you definitely can answer. Like suppose like this question. So you have a module which is a multiplexer of two data D0 and D1, and you need to write a module which is a multiplexer of four data D0, D1, D2, D3. So you just need to write code here. And then for each such question, like I have a test bench which checks that your module works. So what you do is that you simply go to the terminal. And in terminal, you can see scripts. One script is run Linux Mac, and another is run Windows. So if you run it under Linux, like run Linux Mac, or like in Windows, you can do this in terminal, or you can do this in VS Code. It's all like up to you. So you do like run Linux Mac. So this shows you how many of these things fail and how many of these things like it didn't fail. You see, and once you put here correct solution and run the script, it will tell you pass. You see, so yeah, so you just need to get this repository and install a thing called Icarus Verilog for Windows. So Icarus for Windows is a Verilog simulator. So what you do is that you just get like a Verilog version v12 setup. So you can like try it now or try it later. So you get the Icarus Verilog, and then you go to GitHub. So you go to Verilog Meetup. So you go to it's actually more stable version is in Verilog Meetup repository, and this repository is called System Verilog Homework. Yeah. So what you do is that you simply clone this repository. Oh, does everybody have Git installed on the Windows? Like everybody, okay. Is it installed with the option run Linux utilities or not? So if it install an option, then you can use it like VS Code to terminal the same scripts because they will just run a bash which is inside Git. Or how many of you use Windows subsystem Linux? Some of you, okay. So you can do this also on Windows subsystem Linux, but if you do it in Windows without WSL, scripts may conflict with bash interpreter in WSL, in which case you need to use the bash for GitHub. But I think that you can figure it out. Yeah. If you don't figure it out, ask me, I will help you. So You just need to install a Icarus. Huh?
Do you have any recommendations?
They can use either one.
No preferences.
From my side, for general stability, I prefer everybody to use Git to use Bash for Git, so Git Bash, because if you use Git Bash, you don't need to use WSL. The main problem with the WSL is not simulation. The main problem is when you need to program FPGA board on the WSL, and this is true for both Xilinx, Altera, and Gorin. You need to do some extra commands to propagate USB ports of this whole thing. So this is like additional hassle. So like basically I try to like avoid those hassles. Yeah, but you can install it everywhere and then run first exercise, get pass, and then run like other exercises. So I'm preparing a repository with some new questions, but you can now try question in sequential basics. So this like question is that suppose you have block which has input A and which has input B. Okay, let's see if I have this in Wavedrome. Oh no, that's actually a different thing. 1 second. I think I have it here. Oh, okay. Room. Yeah, this is what I wanted. Yeah. So Wavedrome is a software written by like one of my friends, and this is very useful for. So why doesn't show anything? It doesn't show anything because it has something in here. Unexpected. Okay, I need to. 1 second. It should have bracket before signal. Yeah, this thing bracket was not copied. Yeah, so this is my like interview question, which you can try to think about before tomorrow. Yeah, they should use the same zooming link. Yeah. It's a bit.ly/Yuri-Panchul-zoom. Yeah, so this is like you have block which has input A and which has output B. So if and we call token is if you sample 1 on positive edge of clock. So if we sample 1A, we need to produce 2B. If we sample A 2 times, we need to produce four items. If you sample A, then 1 token, then nothing, then another token, we need to produce 4. If you sample 3 and then 1, then we need to produce 8. So if you sample like million tokens, we need to produce 2 million tokens. So and write a Verilog design which has just like 4 signals like A, B, clock and reset to do this. Yeah, but your design doesn't have to support infinity because you cannot do this for infinity, but it can support like up to some n transactions going back to back. So this actually the interview question you can think about, and then what you do is that you go to this repository, and this repository sequential basics, and you go to this like double token. Yeah, so you just modify code here. So you just put your solution here. Then you go to directory which is sequential basic, and then you just run here a script. So this has a script called run Linux Mac. So you run it and you get a failure. So your goal is to make it pass. And once it passes, you can show me a solution. Yeah, so what I found, the question sounds simple. So you have like 1 bit input, 1 bit output. But then I saw some senior engineers who were writing like 2 pages of finite state machine, and it still like it didn't work well. So you can exercise on such things, and by exercises you improve your skills in sequential logic. So we'll talk about this tomorrow. I'm just like telling you now what to like install. Yeah. So you install. In fact, I have. Yeah. So what you do is that you go to GitHub in Verilog Meetup repository. And you look to the pinned repository. So this one, basics, graphics, music, it's to work with FPGA boards. This is one. Second is system Verilog homework, is those exercises in simulator. Third is the system Verilog microarchitecture challenge for AI number 2. And tomorrow, UC Santa Barbara student will talk about this. And another one is called TT Sky Verilog template for Verilog Meetup. And in this repository, I just put set of files which allow you to move your design you created for this board in FPGA into tiny tape-out ASIC. So I put instructions, so you probably all get this instruction. So essentially what you need to do is that you need to replace file laptop in this repository with the file laptop you created for FPGA. And then you can check in this change into your clone, like into your repository created from this like template, and this will cause GitHub actions that runs synthesis and synthesizes this code all the way to GDS2 file. And then you can put an order for tiny tape out and create your own ASIC chip. So just to put it into perspective, the cost of manufacturing ASICs is very different based on volume and technology. So the fixed cost for manufacture of like high-end like ASIC, like 3 nanometer, like 5, 7, we're talking about tens million dollars for only fixed manufacturing cost. We're not like talking about like design, EDA tools, and so on. Then it's much larger numbers. For ASIC with like 28 nanometer for commercial ASIC, we are still like talking about like more than $1 million. But for ASICs with the older technologies, the numbers are lower. And then we are going into numbers for shutter projects. So shutter is a multi-project wafer. So did you learn about this? So you did learn about, yeah, okay. So essentially foundries use their like extra capacity to make some inexpensive like ASICs for a few items, and they cost from like several $1,000 from like $10,000 for 130 nanometer process to like 40,000 for like 28 of nanometer process. So essentially what like Tiny Tape Out did, they simply say that like, okay, eFabless, a company which is a broker between users and foundries Skywater, they sell manufacturing of one ASIC for $15,000. So right now it's a cheap foundry IO. Before they were called eFabless and they were selling it for $10,000.
Last year, eFabless died and they replaced it with eFabless.
Yeah.
It seems like now there's a vendor called Cheap Foundry.
Yeah, cheap foundry IO, yeah. So yeah, I mean, those are same people, so they went out of business, and recently they published that they have negotiated deal of buying assets of former eFabless. So you can do it. But Tiny Tape Out can do this not only through cheap foundry IOs, they also can do it through a German foundry, which is their like alternative source. But the bottom line is that they get students like you, and they get like 50 or like 100 of them, and then they split the cost of this $10,000 to those like to those like 50 students. So like everybody pay as little as $50. So you pay just $50 for one tile, and then you can order a board which cost like it used to cost $250, and now they sell it for like €300. So so here I put actually instruction how to do this. So you can put your design into their infrastructure right away. And in fact, I like encourage you to do this. If you want, I also brought here like 100 of these tiny VGA parts. So if you order a board, you can connect it to VGA and put your game on a VGA. So I have a box of such components here. Yeah. So like I ordered them in China on a factory, so they sell it for like very cheap. It's like a few bucks. Yeah. So essentially here you can buy a board with your oven ASIC for €255. Yeah, and then put on such board. So whatever design you make tomorrow, I encourage you to do it not only on FPGA board, but put it in ASIC. And now, so presenters who will be in just like 5 minutes will tell you some theoretical base behind all this process in like ASIC design. One of most important things you really need to know is about static timing analysis. So how many of you learn about static timing analysis, like propagation, delay, like setup, hold? Yeah, so some people didn't learn, so this is important. So basically, people like me who are front-end RTL designers essentially get paid for the following. We construct a pipelines to process whatever we process, like instructions, triangles, Ethernet packets, and so on. So we build a pipeline in a way that we have to balance how many pipeline stages we have versus maximum frequency. So you can do more combinational logic every clock cycle, but you can have less cycles, or you can make many cycles, and you can do just a little bit, but then you run clock faster. So this is one of the main challenge of a RTL designer slash micro architect. So we need to create some computing structures, and we need to balance between frequency, latency, and bandwidth. So this part is frequently sort of missed in like introductory classes, but you need to know this very well. And the presenter who will talk about like ASIC will talk about this. And now, before he starts, let me just point you. So what I want to install on your computer like right now. I mean, not like right now, but like, before tomorrow, before end of the day, I want you to go to Govin Semiconductor website. So you're going to Govin, and you do Govin download EDA. So you create your account. So you just register account. So govinsemi.com. You register account, then you need to load. So 2ZD, no, 2ZXD, 2ZXD. Yeah, so I created the account. Yeah, so once you go here, what you do is that you go to product Govin EDA, and then you put here download Govin EDA, and then you do Govin Education Windows 64, or and then you click here and like download it. And then you like install it on your computer. And once you install, you can work with those boards. And if you have Linux or Macintosh, you can get like education for Macintosh or like education for Linux. So unlike Xilinx, which doesn't work on macOS, Govin does work on macOS. So then, and you can actually try this at home. So you can just you can get like one of these kits. So you can just borrow it, but like make sure to like return it, or like you can buy it if you want, like you ensure. So in those kits you get this lower part, and in this lower part there are only 5 wires you need to connect. So you need to connect it. You need to connect it according to instruction on the website. So you go here, and you go to the section and update on FPGA board setup. So this shows you how to connect 5 wires to this TM1638 based interface module.
You said you're going to cover the different infrastructure. Please show us how to change them now.
Yeah. This is what I'm going to do. Yes, like I will show the whole infrastructure. I spent 1 hour to going through all scripts, what they are doing, wrappers, what they're doing. Then I have tons of new boards, including some. So you can tomorrow contribute to this open source project by adding your new board for it. You know. So you connect those 5 wires, then you insert LCD. And you can play with those boards. So like feel free to take those kits, try this at home. If you don't try it at home, we can try it tomorrow. Yeah, and once you do exercise, so I recommend you to do some basic exercises and some like exercises with the graphics, and then tomorrow we will try exercises with like graphics and with microphone. Try to put it into ASIC infrastructure, and then I will also give you interview questions, and if you have dry erase board, maybe with somebody I can do review of what like you're doing, so we can make exact assessment how much Verilog in handling sequential logic you learned so far. This is like very important, because you may think that you learn already everything, but then like but then you realize that you simply missed some like important point. This is just like a trainable skill, you know. You basically, when you like play flute, you just need to practice gammas until you play melodies. And if you just watch presentation how teachers shows how to press like buttons, you will never learn. So this, you need to like train yourself with such exercises, and then you can have a very easy life, like during interview and like start of career. Okay, so I think that we now need to connect our participants, and they will talk about this ASIC infrastructure. So does anybody have like any questions?
Cal Poly wants to use Greek logic.
Huh?
You mentioned that Cal Poly has a preference for Greek logic FPGAs.
No, not for Quick Logic. This is a microchip, which is former Microsemi, which is former Actel. No, they not have preference. They just want to replace with Francisco. Hi, can you hear me?
Yes. Hi.
Yes. Now, like I can hear you, so we can, yeah, we can hear you. And okay, so let me also connect. So let me also connect Henry. Let me make sure that everybody can share the screen.
Yeah.
Huh? So what? Yeah. So you can share. You can share your screen if you want.
Yeah. Let me just make sure
but
this
how
comes
to?
up. Huh?
Oh, we need to connect sound. So how to connect sound?
Yeah. Let me know if can you guys hear me in that room and see my screen?
Yeah. The problem is that this shows that I don't have sound. I don't have video. I mean, you can connect another computer. Okay. So sound. Okay. You have. Oh.
Yeah, look at that. That's the little arrow here.
Mhm.
It has one of those.
No, this actually doesn't have it. We can connect a different computer. Maybe we can connect your computer and do it. So let's just connect your computer and you're there on Zoom, so you just connect it there and do it. Okay, so what is your preference? Do you want tomorrow to start with doing things on FPGA, or doing things with simulation, or doing a little bit of both? Okay, so let's start with FPGA. And about interview questions, I will just give you everybody some PDF, because and I want you to just write me code and check with this thing. And once you write code and check, I will review your solution. We will talk about your solution. So I will just send you link, and you will try to do this. And then, like at the end of the day, I will. Yeah, but like again, I ask you to do this using yourself and not using LLM, because with LLM, like it doesn't teach you anything. But then we have interesting discussion, like informative. Okay, so can you? Yeah. So let me. Huh? Yeah. Okay. Let me admit. Yeah. So this is suggest. Yeah. So like I encourage everybody to install Govin on your systems tomorrow. And if you don't, you can use like I have some extra computers. So like if like anything doesn't work, yeah. Yeah, and I will actually put this stuff back into my car because we need to get out of here at 4 o'clock. Oh, but
Hello?
one second, I will turn off.
Hello? Victor, do you have your sound on? Or your mic on? No, I can't hear you. Oh, you might have to switch mics.
Can you hear now?
Hi. Are you getting feedback from this now?
Yeah.
You are?
Okay.
Hello. Okay. No feedback? We good?
Yeah, we're good.
You guys ready? Okay, well, hi everybody. Hope you're enjoying your hackathon so far. Victor, would you mind turning the laptop around so I can like see the audience a little bit? As much as I like this wall.
Sure. Here.
Okay, wonderful. Wow, that's a lot of people. Hi, everybody. Nice to see you. So a little bit, just to start, I'll give a little intro. My name's Francisco, or Cisco. I graduated last year from Cal Poly with a master's in CS, but, you know, CPE undergrad. And last year I taught a tech collective class on open source ASIC design. So maybe some of you took that, maybe others of you heard of that. And now I work at a semiconductor company called Astera Labs doing design verification. And today I'm going to talk to you basically about ASIC design and how it relates to and differs from FPGA design and some of the lessons that we're going to be able to take away from that. So to get started, we're going to be talking about the entire design flow that it takes to create a chip from System Verilog, right? So we're going to start with RTL, which is, you know, the code that we write to describe the behavior of our digital circuits. And we are going to, through a series of many, many steps, turn that into a GDS2, which is a final database that describes the complete circuitry of a chip. And this is a really advanced process. We're not going to do all these steps by ourselves. Instead, we're going to use a tool flow to kind of do all these things that we need to do to turn our design into a chip. And as chip engineers, we have to kind of understand at a high level all the steps of this flow so that we can understand how it can fail and the kind of things that can go wrong that we need to fix. And this is kind of different than our normal experience working with FPGAs, because with FPGAs, all of these steps are bundled into one tool. Like we have a tool like Vivado that is going to do all of these steps, and whereas in more ASIC related tool flows, we're often using many different tools from many different vendors to accomplish different things, right? So for today, we're going to be talking about mostly open source tools because that's what is available at the academic level. So to start, we're going to talk about OpenLane, which is kind of the most modern open source chip development tool that we have. More recently, it has been renamed LibreLane, as it has kind of been changed owners of who is working on this tool. And that's going to be the main VLSI tool that we talk about today. So VLSI, or very large scale integration, is this process of taking our design and turning it into millions or billions of transistors, which is, a very complicated process. And to do that, we're going to be working for a specific manufacturer, right? So unlike FPGA design, where you can kind of write Verilog code and then pretty easily transfer it between different FPGAs, every time you are porting ASIC code between different manufacturers, there's going to be some heavy changes that have to occur on the kinds of gates and cells that you're allowed to use. And so we're going to be talking about mostly using the Sky 130 PDK, which is provided by a foundry in the United States called Skywater. And they have made their process open source so that anyone can look at what their cells are and what their kind of silicon manufacturing process is like. And from that, we can access everything we need to make a chip. And so to start this process is something that happens on both FPGA and in ASIC land, which is just linting. And that is just making sure that your code doesn't have syntax errors. So, no missed semicolons, all your widths of all your signals are what they're supposed to be. This is kind of the first easy step that we can do to qualify that our code is of quality. If we're used to using Vivado, it's kind of not a very strict linter, and it will let you get away with kind of whatever you want. You can have signals that are different widths and just tie them together, and it'll kind of assume for you. In the open source world, we use Verilator as the primary linter, and Verilator is a much stricter tool where anything that you don't do completely up to System Verilog spec is going to get mad. And the idea with this is that we want to catch issues as early as we can in the chip design process because it's a long and iterative process. So we don't want to, miss a semicolon somewhere, miss a begin end, and then suddenly our design is falling apart, right? So the first step of this is getting used to kind of working in stricter syntactic rules for writing our code. And once we have linting code, we can take it into simulation. So we are familiar with this in Cal Poly Vivado land. You hit your simulate button, you produce some waves, you say it looks good to me, and you move on. So simulation is very different in the FPGA and ASIC world in how it is used. In FPGA land, simulation is useful, and you're going to want to do it to qualify your design, but it's only a check because it's pretty easy to just hit build, put your code on the FPGA, and see if it works, right? You don't really have to be completely 100% sure that it's working. Whereas in ASIC land, simulation is where we spend most of our time, right? It is our main iterative process of development, is pushing things into simulation and trying to cover every possible corner case and hit all the checks that we need to check. And to do that in the open source world, we're actually going to make use of two separate simulators. One is called Icarus Verilog, and the other is Verilator. Icarus Verilog is a slower simulator, but more accurate. It can cover more states, including X, which is unknown states, and high Z, which is an undriven wire. It can cover states that aren't just 1 and 0, whereas Verilator simulates a lot faster, but can only treat things as 1s and 0s, which makes it less accurate for figuring out if your chip's actually going to work. And so both of these are important tools that we're going to use. And similarly, in industry, we will also take simulators from different vendors, maybe Cadence or Synopsys, and make sure that things are working across different vendors. And so continuing in the same process, FPGA and ASIC both are going to head towards synthesis. And so this is where we're going to take that RTL code that we wrote, and we're going to turn it into a lowest level logical equivalent circuit, right? So this is going to map all of our operations into NAND, NOR, XOR, those kind of like lowest level operations. And from there, our paths for FPGA and ASIC kind of diverge, because FPGAs are full of LUTs, or lookup tables, which are these homogeneous blocks that can be, that can say for any input, I'm going to create a certain output, right? And so we're going to use a lot of these same block over and over, just programmed in different ways to create any logic that we want. And so there are some exceptions to that. In FPGAs, we do have kind of specialty tiles that we use for maybe multiply and divide and complex operations. But for the most part, everything is a homogeneous kind of same size LUT, right? In ASIC land, it is very different and very dependent on the manufacturer you're using, right? So the manufacturer that you are using will provide you a PDK that defines standard cells. And these are like our lowest level units of logic in ASIC land. And they can be really tiny or really big. So on the bottom right here, you can see we have a really tiny inverter and a really big full adder. These are both lowest level units, but they can widely vary in functionality and size, right? So where instead of this homogeneous kind of big array of the same size blocks, we have a lot of variation in size and functionality that we get to play with and choose, or rather our synthesis tool gets to play with and choose. And in open source land, that's going to be Yosis, which is kind of the only open source synthesis tool that is available. And so here's where we start to diverge in terms of FPGA and ASIC development. And that is this idea of gate level simulation. So after synthesis in FPGA land, we would just take our design, put it on our FPGA and run it, right? But when we're designing an ASIC, we actually really want to make sure that that synthesized output that we get completely matches the input RTL that we gave it, right? It would be really bad if we described a design and then the gates that came out of it didn't perfectly match in functionality. So we are going to actually rerun all of the tests that we wrote on our original code on just the gate level netlist. So this netlist is another Verilog file, except instead of having behavioral code, it only has instantiations of lowest level logic gates. And so if our design is, just an adder, we're going to run our same tests of trying to add numbers through our code and our behavioral model of these cells and make sure that the result is the same. And so this process is very time consuming and important in ASIC development to make sure that the thing that you're making actually works. So we're going to see a lot of simulation in this process to make sure that our advanced designs are actually working. So now that we have a synthesized design and that we think that works, we're going to do static timing analysis on it. And I'm not going to go too into depth because your very next presentation is going to be about this topic. But the basic idea is that we want our design to meet the timing constraints we give it, and we want to figure out how fast our design is. And if our design is too slow, we're going to have to go back to the drawing board and fix some things so that we can reach our target frequency. And for this, we're going to use an open source tool called OpenSTA. So now that we have our design, we know that it kind of is going to be fast enough. We have to decide what the layout is going to look like. And this is another big difference from FPGA land, because FPGAs are pre-laid out for you. You don't have to make any decisions about where things go, right? In ASIC design, there's a lot of decisions we have to make. And the first big decision is where to put macros. So macros are pieces of other chips that we can reuse, right? So they might be things like RAM. They might be something that you're using a lot of that you just want to repeat. And they can be really big blocks that we have to choose intelligently where to place. And so placing these is going to be really important. And then around these, we will place all the rest of our logic. And when we're placing our logic, we actually have a lot of decisions to make about how much logic to place. So we could fill the entire chip with logic, with transistors, and then we probably wouldn't be able to wire anything up because it would be too dense. So on average, we are only using 50 or 60% of the area that we have available, and we have to intelligently make decisions about how much of this to use in order to have our designs be successful. If we use too little, low utilization, we won't be able to fit all of our logic. But if we use too much, then we might not be able to connect all those pieces of silicon with wires. So it's important that we pick something in the middle of the road here. And so instead of just having a set amount of LUTs that we get to use, so maybe you're on an FPGA with 10,000 LUTs, we actually have a very variable amount of room, even on the same size chip, that we have to play with, right? And so once we have a general idea of where things go, we have to lay out a power distribution network so that everything on the chip can get power. Here's another big difference from FPGA. Because in FPGA land, we do care about power, but only as much as it costs us money. So if you're running a server that has a big FPGA, you're paying for that power, but you don't really worry about that FPGA melting, right? With an ASIC, you can have a lot of power in really high dense locations, and that can cause your chip to melt and be physically damaged, right? And so we have to make more design decisions in terms of, do I want this part of my design to be on, right? If you're designing it like a pipeline with a multiplier and you're only using the multiplier some of the time, we might do some kind of trick to turn that multiplier off while it's not being used, right? So it's important to kind of consider power and make sure that everything is getting connected to power as we're designing a chip. So then we have kind of our basic layout of our chip. We know about where things are going to go, but now we have to actually choose a position for all the millions of gates that we have. And so instead of just having connect up pre-placed LUTs, we get to make a lot of decisions, or more realistically, the tools have to iterate over these positions of all of our gates in a way that lets them be connected and fast. And so to do that, usually we're going to use some kind of like gradient descent kind of algorithm, similar to what AI does. And that's going to optimize where all of these cells are living. And so we're going to kind of find approximate places for them, and then we're going to map them to a grid in a process called legalization. So on an actual chip, all of the cells are in nice standardized rows, and so that's where they're going to all end up. And unlike most signals, which can just kind of be local, there are certain signals that have to make it across the whole chip at the same time. Specifically, the clock signals are a great example of this, where it is very important that they arrive at the same time across the chip. So one side of the chip and the other side of the chip are getting the same clock arrival signal, right? And so to make that work, we have to do a process called clock tree synthesis, which uses specialized structures to distribute this clock evenly. Often it's going to be a big mesh that looks kind of like a fractal, where the clock is going to enter at one point and then exit at the same time on all the leaf nodes of this big tree. And we do this to minimize the difference between the times that the clock arrives in different parts of the chip, because those differences can make our chip break and cause timing violations that will be discussed later. And so now we have all of our gates are on our chip, and they're placed, and they have a clock coming to them, but none of them are connected to each other. And so this is what the routing process entails, is how we actually connect those gates to each other. And this is a very time-consuming part of the chip design flow, because there are a lot of wires in a chip. And most modern chips are way more limited by how many wires they can fit than by how much physical, like logical transistors they can fit. Connecting everything together on these really big buses takes a lot of work. And so routing is going to use many layers of metal to connect everything as needed, with higher layers being thicker, used more for power, and lower layers being very thin and used for like local signals. And so as we are routing, we're going to run into congestion, as certain areas use a lot more wires than other areas. And so if we hit 100% congestion, that means there's no way we can route a new wire through a certain area. This happens a lot at the edges of macros. So as you can see in this image on the right, we have all these big rectangular blocks. Those are macros that have pins on them. And around the edges, they are very high utilization. So there's no way you could route a signal through there. Whereas certain corners of the chip in blue, you could put as many things there as you want, because there's nothing going on there. And if we hit too much congestion, we have to turn down utilization. That means use less gates so that they have more room to be connected to each other. And so if you've ever wondered, like, why does RISC-V stop at RISC-V 64? Because there's, 32-bit, 64-bit. They've even added 128-bit RISC-V. The more parallel wires that you're trying to route, the more likely you are to run into congestion, because it gets exponentially more and more difficult for all of those wires to reach their locations. So when we're designing systems, we have to make sure that the bus widths that we're making, especially if we have separate like address data kind of buses, need to be small enough that they are routable, right? And so that is a big constraint of chip design, is how we can get very wide signals to travel across our chip. And so you thought we were done with simulation when we were making a chip, but it turns out we're going to do simulation a third time. So we did gate level simulation after synthesis, and that told us, does the gates that we chose to represent our logic actually represent our logic? Now we have to decide, do the gates and the wires and all the buffers and power logic that we have created also match the original code that we put in, right? And so after this process of place and route, or PNR as it's called, we're going to get a new netlist, which is going to be a place and route netlist. And that's going to include wires and buffers and things that aren't just logic, right? And that we will put back into our synthesis, back into our simulation, and run and get more waves and tell us, hey, does our design still match that original intent, right? And that is how we really make sure that that final design is matching with what we want it to do. And additionally, we are going to be able to rerun our timing analysis, because now we have a better understanding of how the signals are going to be traveling across the wires on our chip. And so that's great. Once we do those things, we're like pretty sure it works, but we're going to do a final thing, which is to put them together. We're going to put our timing analysis together with simulation. And this is about the trickiest part. This is called timing annotated simulation, or SDF simulation, which stands for standard delay format. And so this is going to simulate all of our logic and then also all of the propagation time. So you can see for this example with a NOR gate that depending on how its inputs are ones or zeros, the time that it's going to take to propagate its output or the delay of this gate is variable based on the inputs that are introduced. And so this is going to give us the most accurate picture of timing as it actually would be on the chip. And so this is a very intensive process. At work, this has taken terabytes of RAM. So when your RAM starts like looking like a hard drive, you know that this process is difficult. So anyways, now that we've done this, we really know our chip is going to work. And so functionally, our chip is working, right? But there's still a couple other things we need to do. So we need to make sure that we understand the kind of timing behavior of the physical design of the chip. And so for this, we're going to do a process called parasitic extraction, where we're going to look at the physical layers of the chip to calculate resistance and capacitance, and use that to rerun our timing analysis. So we can see, based on the sizes of wires and of silicon, we can calculate our capacitance, and that will change what the timing looks like on this chip. So these are things that we can do after the design is complete to have a better understanding of how it's going to work. And just because our chip logically is going to work doesn't mean it'll actually work coming out of the factory. So here's another thing that is very different from FPGA design. In FPGA design, if you put working code on your FPGA, you can be pretty dang sure it's going to run. If you put a working chip on a physical die, you don't know that it's going to work because it had to get manufactured, and some things can go wrong during manufacturing. One of the big things that can go wrong is called an antenna violation, and it's actually not related at all to noise, even though it kind of seems like it would be. It is completely related to static charge buildup that will destroy your gates. So if you have a really long wire, as this wire is etched in metal, it will build up static charge and then possibly destroy the gates that it's connected to. And so if you have a really long global signal going from one end of the chip to the other, this super long wire will pick up charge and then destroy the gates it's connected to. So there's a lot of work that the tools have to do to make sure that these long wires aren't hooked up in a way that will cause them to fail during manufacturing. So this is a problem we can run into that may need design changes if you have really long global wires stretching across your chip. Moving forwards in manufacturability, we have to pass a phase called DRC, or design rule checking. And that just says, is this design that you're giving me actually manufacturable by the foundry or factory that is making this chip? And so it's going to go through all of the little rectangles that define all of the layers of our chip and make sure that they all follow the rules. Are they far enough or close enough apart? Are we violating anything that would break our chip? This takes a really long time because it has to go through dozens and dozens of layers across millions and to billions of polygons and make sure they all are the right size. And then now that we know it's probably manufacturable, we need to make sure that the final design matches what we expect it to. And so for this, we're going to do spice extraction, which is to take we're going to take the physical design of our chip and turn it into a spice model, kind of like that of LT Spice, right? This is an electrical model of our design, and we're going to make sure that it matches what we expect it to, right? If we really want to, we can also simulate this electrically. If we were doing a mixed signal chip or an analog chip, this might be more important. So we could do very slow transistor level simulation. This is not something that we would do for any design of scale, but for really specific blocks, you might want to do an electrical simulation with this spice that you get. But the main use of the spice is to do layout versus schematic, or LVS. And that is just to compare the spice netlist to the input design that we gave it. So does that design that we gave it actually match what electrically has been created? And so sometimes this doesn't match. Maybe we forgot to hook up power to something, or there was some issue in the tools that didn't properly connect some pins. And this is the step that we would discover, hey, even though I described my design perfectly, something didn't get connected right that would cause it to fail. And so if we're able to get through this step, we are pretty much done. So now we're going to go to tape out, which is a big fun word. So we're going to complete sign off, which is basically signing our name, saying I did all the checks. I did gate level sim, I did timing, I did DRC LVS. So I'm ready. And then we're going to send that final design to a manufacturer. And boom, now we have a chip. Well, almost. In 3 to 6 months, we'll have hundreds of chips. And they might not all work the same. Some of them might work, some of them might not work. And so then comes kind of phase 2 of chip design, which is, okay, now you have your silicon. Now we actually have to bring up this silicon and make sure it works. And so this is often kind of underrepresented as how much work this is. It is like, you know, sometimes 30% of the budget of a chip is just making sure these post-design designs actually work. And so there's a lot of work that goes into designing a chip in a way that makes it easier to bring up and makes it faster to know whether or not the chip works or not. And actually tomorrow, as a part of some of the more advanced presentations, I'm going to talk about one of these processes involving memory. But for now, we just had a big crash course on all the things we have to do to turn our design into a chip. And so I think that is it. So hopefully you guys have some questions for me, because I know that was a lot of information. So let's go to a quick Q&A before I pass the mic off to static timing analysis with Henry.
Okay, quick question.
Yes.
When you're doing STA and you want to include the pair of SIGs, is that the spec file you're including? How do you get those pair of SIGs in your STA?
Yeah, so usually it's going to do this for you. I think you're right. I think it is the spec file that will tell you that. But yeah, we'll have more STA presentation pretty soon. So yeah, hold your STA thoughts because that will probably be covered in some way. Any other questions? I know that was a lot, so I'm happy to go in more depth about any of it.
Any thoughts on the open source linting for CDC? You mentioned the Verilog, which is syntax.
Sorry, what was that?
Linting for CDC.
Oh, linting. Yeah, linting for for clock domain crossings.
Right.
Yeah, so that is a feature that is fairly lacking in the open source tool chain, but is a lot more apparent in industry grade tool chains. So as a part of that original lint process, we're going to want to know what signals are crossing between different clock domains and making sure that those signals are properly synchronized. And so a big part of the lint process in more professional tool chains is knowing what signals are in what clock domain and making sure that they're appropriately, like, you as a designer are aware that, hey, this signal that you're routing from one point to another, that's actually in the wrong clock domain. So yeah, that's true. That is a good important piece of lint, but not really covered in the open source tools.
I think there is another very important element for verification that's not mentioned here.
Yeah.
It has nothing to do with simulation.
That it was what?
It has nothing to do with simulation.
Mm-hmm.
What would it be in your opinion?
Are you talking about formal verification or
Has to do with FPGA.
Oh, emulation, yeah. Is that what you're referring to?
Yeah, I think this is, by the way, this is excellent presentation, and I'm planning to distribute it in my contacts, including a team in Sarajevo. But please add a section on emulation, especially given that there are these holes in the open source flow, like CDC that we just identified.
Yeah.
So very important. Simulation is slow, especially when you talk about processors. Very important to, and that's part of the industry approved flows as well.
But listen, just first of all, CT in many designs is kind of new, but also in certain parts of design. The whole CPU core may run using only one clock, and then Coherence manager using another clock. So many large blocks use only one clock. So this is not something which is constant use. There are not so many designs which have very many clocks. Now, this is the first thing. Second, I never heard about emulator used to verify CDC. I mean, there is a verification for CDC in a Spyglass for Synopsys, but I never heard emulator can verify. I thought that emulator is purely functional, not accurate, not for. So,
well, I'm not saying it's going to catch the CDC, but by the very fact that you can run longer synthesis, the chances of catching
longer runs that
right.
You can put Linux on not yet a manufactured CPU. No, this is a certainly important topic, but this is not part of the RTL to GDS2. This can be part of RTL to GDS2 presentation if you make it not 1 hour, but if you
if people are using this flow to actually take out an actual chip, then they are missing out big time.
Not really, because I'm not aware of uses being used for something like a large SoC with GPU, hand and so on. It's used for smaller projects. And for smaller project, emulation is not as relevant. Like we have to use emulator in Samsung because otherwise you cannot simulate even a single tray properly software simulation test. And like Intel has to use emulation because otherwise they cannot run like a beaten.
How about this? Okay, very simple project. Your games, right? Can you simulate? Yeah. You can simulate the games fully.
Yeah, so we can even simulate.
Hear the question?
So
Right up there.
Sorry, what was the question? There's, yeah.
Are there open source tools for black or logic equivalency check?
Yeah. So you're talking about like tools like Formality from Synopsys?
Conformal? from
Yeah. Yeah. So there are
Basically,
formal.
like making sure that your synthesized gains massive RTL.
Yeah. So there are formal verification tools that can do some logical equivalency stuff. So that includes there's like Yosis's SBY, I think, is a good example. But I think as far as like tools that are designed just for logical equivalency, I'm not completely familiar with what those tools are in the open source space. I'm not sure that there are as good of tools there, or like the same kind of tools there that there are in industrial flows.
Well, that's not so surprising because they're extremely expensive.
Yeah.
I was just curious, but that's good that they're working on it.
Yeah, I think there's definitely a lot of holes in the open source tool chain. On the one hand, on the other hand, for smaller, for the scale of designs that are usually being done, it isn't quite as big of an issue because it's just easier to cover more of the corner cases yourself in simulation.
Okay, thanks.
So for formal, there is a company called Symbiotic EDA where they call the folks who work with like Yosis and with this tool chain like work. And if you go to website Symbiotic EDA, they do have some formal tool for like assertion checker, but the problem is because they don't at least they recently they didn't have a complete system Verilog front end, so they couldn't cover all system Verilog assertion language, so they had to use some like preprocessor limited version of it. So yeah.
So I don't mean formal verification.
You
I'm talking about
just use it like logic equivalence check.
Yeah.
It's like light thing. But also I'm not aware about like for the open source lab. Yeah, but you see, for like specifically our audience at the moment, it's not very critical at the moment because when students create student projects, they don't really need lag. We need lag in like industrial companies because if we miss a bug, this can end up with like a $20 million respin, like on a farm, and even much worse. If company have to do like several respins, like it can miss the time of market and all money will be eaten by competitors. So when like multiple companies go to the market with similar chip and one go a few months earlier, it can eat all the revenue projected for like other chips. So for this reason, for like industrial company, it's very important to protect as much as possible with like everything they can, including lag. But for like students to run lag on every single project is just additional hassle, which doesn't add to like understanding of like microarchitecture, doesn't seem.
But But what I like about the open source tools is I think the better they do, it pushes the commercial companies to make their tools better or more affordable or, I mean, it's good when open source starts to, they have a long ways to go, but if they start competing with commercial tools, maybe for smaller projects, then that creates some urgency for the commercial tools to get better or maybe come down in price or so.
Oh, I completely agree that
that's-
Slack evaluator, I completely agree that things like evaluator, which is a high performance simulator, does put pressure on synopsis and cadence because when you have something for free and another way you charge like tens of $1,000 or heavy subscription fee, then obviously there is problem. But with more like niche tool like that is not as much, not as much respect for it. But it's kind of interesting discussion.
But here's what I think. If it's important to highlight the capabilities of the open source tools, I think it's equally important, maybe even more so, to basically single out the gaps, the shortcomings, at least for the people to know what, what to pay attention to. At least to know that there is a normal industry process and part of this process to prepare for industry, right? Interview process, stuff. At least, no, so normally in the industry, people run Link CDC. If they don't, they cannot sign off, as simple as that. Say that such a step exists, it's not covered. So it has to be covered by other means, maybe by very careful review, peer review, things like that. Or also highlight that is part of the normal industry process. Emulation is part of the normal industry process. We are not covering it for whatever reason, but at least, people who are listening to a presentation and who want to use presentation to take out their own shit, they know what they are, and they will think about how to make up for that for short time.
Okay. So let's move to this presentation. We have more of these discussions tomorrow.
Yeah. Yeah, I guess so. If that's it for questions, we'll move on to Henry's presentation on static timing analysis.
Thank you, Cisco.
Yeah, thanks for listening. Feel free to contact me with any questions you have.
Yes, this was actually very clear and like a concise lecture with all the important information, kind of a minimal shrink wrap information necessary. Like, for,
Yeah, there's a lot, but it's good to get it all out there. But yeah, thank you for the opportunity to speak.
Yeah,
Take care.
like from point of view of like front-end RTL designer, this is like a necessary minimum to start designing like pipelines, balance latency versus timing and so on. Yeah, this is like great. Certainly for physical design engineer, you need much more, but we are now trying to get students into microarchitectural design. Yeah, and prepare for the for such like jobs. Yeah, so this is great. Thank you.
Yeah, thank you.
Okay. Yes, Henry.
That sounds good. We can hear you, Henry. Oh, yeah. All right, give me 1 sec. What? Now it works? Yeah. Okay, I'll take it. All right, give me 1 second, get all set up.
Yes, we can hear you.
Okay, can you guys see my slides? I see a thumbs up. I'm going for it. All right. Cisco, can you turn off your speaker? Thank you. Hi, my name's Henry. This is going to be a quick and dirty introduction to static timing analysis, or STA. This is not going to be super in-depth. It's not going to be quite as in-depth as Cisco's presentation. I'm hoping to do a follow-up presentation tomorrow on some of the more advanced static timing analysis concepts. But for now, this is an introductory course that you can understand if you've taken, or presentation that you can understand if you've taken like 133. Or digital. You guys are on semesters now, so now none of my course numbers match up. So intro to digital design. Hi, like I said, my name's Henry. I'm an electrical engineering graduate who graduated this year with a master's. I just moved to San Jose to start working at a silicon engineering company called Astera Labs that does cool stuff like PCIe switches and CXL controllers and retimers and all sorts of fun stuff like that. And when I'm not at work, which is granted a lot of the time that I am at work, I like hiking, camping, outdoorsy stuff, baking, working on bikes, stuff like that. Anyway, with that out of the way, let's just go cover this a little bit. But in your digital design courses, we like to think of, all circuits as ideal. All signals propagate instantaneously, and all flip-flops can sample instantaneously. And it would be wonderful if we lived in a world where that was true, because damn, we could make some really fast processors and chips. But that's not the case. Because we live in the real world that we do, we have to deal with parasitic resistances and parasitic capacitances in our transistors and our wires and our components in general. Can you guys see my cursor, by the way, on the slide? Moving it around?
Yes.
No? Okay. Let me give me like 2 seconds to try something.
It's out there. Just make it big.
Okay, that's fine. I'll just tell you what I'm looking at. So you can see on the bottom. Okay, you can see on the bottom, like, so all the transistors in this is a CMOS NAND gate. All the transistors on this design have some amount of capacitance, both on their input gate and just on the source and drain. Just because, again, we live in the real world, everything has some amount of capacitance. And they also, because they're not ideal, there's some resistance to the current that flows through them. That means that every component in our design effectively acts like a tiny, tiny RC, or resistor capacitor circuit. Those of you who've taken circuits too will know that that gives us a rise and fall that looks like this graph, or this oscilloscope graph I have up here, where you can see the green line is the sort of idyllic, the signal switches on and then switches off instantaneously, whereas the yellow is the more real world. It takes some time to come up to the full voltage and some time to drop down to 0 volts. Every component in digital design has this characteristic. And we can make that characteristic more pronounced if we have things like long wires, because they add a lot of capacitance and a lot of resistance. If you have a wire that has a large fan out, so it's driving a lot of gates, that also increases the delay, because each gate has its own capacitance, so that net is driving, in turn, more capacitance because of that. Gates with large fan-ins, interestingly, also have larger delays. That's because if you see this on the diagram I have up there, the 2 transistors that are wired in series at the bottom. All right, as you add more inputs to that gate, you have more of those transistors in series. And so their series resistances start to add up and increase the delay that's associated with that gate. And there's delays from things that aren't just gates. Wow, this picture's really pixelated. Bear with me. One source of delay is clock to Q delay, which we don't worry about a ton because we can't do anything about it. It's just an innate fact of using flip-flops, but there's a delay between your rising clock edge and the data being propagated from the input of your flip-flop to the output. So that's something we also have to worry about as a contributor to our delay. Okay, there's all these delays, right? It takes time for signals to propagate. Why do we care? So we can represent from a static timing analysis perspective, right? We have all these complicated designs. We don't care. All we care about is we have a flip-flop, some combinational logic, and then another flip-flop, which, is drawn up on the screen here. And the core rule of static timing analysis is that for every single path through our design, it must be able to complete within one clock cycle. And that's because if it can't do that, then, the data will launch from flop 1 on one clock edge. It won't be available to flop 2 when flop 2 receives the next clock edge. And so it will sample old stale data. And our design just won't work at that point. So static timing analysis is at its core, there are exceptions to this, but as its core, just double checking that every single path in the design meets this requirement. And there can be trillions of transistors in a design. So there can be, or a trillion transistors, I think. So yeah, there's a lot of paths to cover here, which is why we use tools to do it. Okay, and there's one more. There's one more contributor to make this process more difficult. I didn't cover this when I was talking about delays, because technically this isn't a source of delay. This just makes it harder to meet timing, so to make sure that all our paths can propagate within one clock cycle. But that's clock skew. Cisco talked about this briefly, so I'm not going to talk about it too much. But basically, we have one signal, which is our clock signal, that needs to reach potentially every single flip-flop in our design on chips that are like millimeters wide, right? Or in some cases, centimeters wide. And so it doesn't necessarily arrive at all the flip-flops at the same time. This leads to what we call clock skew, which you can see on this diagram in the bottom left. We have clock A, clock B. They are offset by a little bit because of that clock delay buffer in the schematic. And so in this case, right, we can see that the data will launch from register A at the first rising edge of clock A, and then it will be received at the next rising edge of clock B. Now, in this case, you can see because of the clock skew, the rising edge of clock B actually happens later than the rising edge of clock A. So in this case, we actually get a little bit of extra time. Clock skew is actually helping us meet our timing requirements because it's giving us a little extra time for that signal to propagate. There are problems with this, which I will get to in a second. This is definitely not good. But what we talked about so far, this could potentially be helpful. But imagine for a second that clock skew goes the other way. Imagine that clock B is going sooner than clock A, right? That clock skew subtracts from that window we have between the rising edge in clock A and the rising edge in clock B and cuts into our timing margin. So for this reason, it's really important that all the clocks in our entire design, which again is, tens or hundreds of thousands of flip-flops, all arrive at the same time. For that, we have a clock tree. I have a diagram of a basic H clock tree up here now. The benefit of the clock tree is basically if you can see the clock input and you can see some of the flops right around the clock input, there is, in this case, 1, 2, 3, 4, 5, 6 delay buffers, those little arrows, between the clock input and the flip-flop, even if it's really close to the clock source. And there's the same number if it's really far from the clock source. So the goal here is there's the same number of buffers between you as a flip-flop and the clock source, regardless of where you exist physically on the chip, because that minimizes clock skew and makes sure the clock arrives everywhere at the same time. Okay, I said earlier that all signals must propagate in one clock cycle or less. That was a lie. They actually have to propagate in less than a clock cycle because of what's called setup requirements. So flip-flops, being the imperfect devices that they are, actually need a little bit of time before the rising clock edge to sample their data. So the data has to be available at a certain amount of time before the rising clock edge. Not at the rising clock edge, but before it. This means we actually have less than one clock cycle to propagate our signals, again, eating into our margin. That's going to be a running theme here. We just have several things that continue to eat into our timing margin, making it harder to meet timing. The big way you can solve setup requirements is you can decrease the clock frequency. So if you have a design and you're trying to run it at, let's say, 2 gigahertz, and you're just not meeting timing, you can say, all right, 1.5 is fine. We'll just do that. And you can do this even after the chip is taped out. If you made a mistake during static timing analysis and you get the chip back and you realize you're not meeting setup requirements, you can just decrease the clock speed. And it'll still work. And this is done to an extent by companies in a process called binning, which you may or may not be familiar with, which is basically where they say, all right, some of our chips are good, some of them are okay, some of them are bad. We're gonna take the okay ones, sell them, run with a lower clock frequency, sell them for cheaper, make some of our money back that way. Okay, now hold requirements. This isn't something you've probably talked about at Cal Poly unless you've taken like some of the VLSI courses here. But the other imperfection with modern flip-flops is that the inputs have to be stable for a little bit of time after the clock edge too. So after the flip-flop samples the data can't change instantaneously, right? This means that there has to be a minimum delay from the launch of the data from our source flop and it arriving at the destination flop. If there isn't that minimum delay, if that minimum delay requirement isn't met, then the data can update too quickly going into the destination flop, and the destination flop might sample the next cycle of data. This can result in data sort of racing through flops. So if you have a series of flip-flops back to back to back, and you have a hold time violation, the data might race through multiple flip-flops in a single cycle. As you can imagine, this leads to incorrect behavior on your chip. This is definitely not what you want to see. And the really scary thing about hold requirements is that they cannot be corrected post tape out. So you might be thinking, well, if setup requirements can be fixed with, lowering the clock speed, and hold time requirements are kind of the opposite thing, maybe you can fix it by increasing the clock speed. That is not how that works. If you have a hold time violation and you tape out, that chip is, maybe you can salvage it by just not using the functionality the hold time violation's in, but potentially you just have a dead chip depending on where that hold time violation is. So these are very scary. So how do you fix them? Assuming you notice them before tape out, you can fix hold time violations by inserting delay cells between the source and destination flip-flops. So these are also called buffers. Their only job is to introduce delay to the signal, so it takes longer to get there. And you see this most often with things like shift registers, where you have no logic between two flip-flops, and the data just goes from the output of one flop to the input of another with nothing in between. Okay, what happens if you break these rules? What happens if you violate hold time or setup time requirements? So what happens then is the flip-flops might sample some random in-between voltage. It is neither a 0 or a 1, but let's say you're running at 1 volt, they might sample 0.5 volts, which means that flip-flops don't like having an in-between voltage in them just by their physical design. They will eventually resolve to a 0 or 1, but you don't know which. So your chip will effectively have random behavior in that part, which makes it extremely difficult to debug. Fun fact, there are actually some circuits that take advantage of metastability and it's intended. The primary one would be like a true random number generator. Will often take advantage of metastability because it is a random process and it can create truly random outputs. Outside of that, very limited case, metastability is very bad and again, can totally kill the functionality of your chip. Okay, let's talk about corners. So because that's a typo, ignore that. Because not all chips that come back are going to be exactly the same, you have to test across multiple scenarios whether you're meeting timing or not. So some things that can affect this include manufacturing variances. Manufacturers, like flip-flops, are not perfect. Basically, the entire theme of static timing analysis, we live in the real world and nothing is perfect. Manufacturers are going to have variances from die to die and wafer to wafer, and you have to make sure you have the tolerance built in for that, or else some of your chips won't work. Some of them might work, but you want as many as possible to work because taping out is expensive. Operating temperature. The speed at which transistors switch varies quite a bit with operating temperature, and you need to be validating across multiple temperatures. Voltage. One thing you can do if if you are not meeting your setup time requirements and you can't decrease your clock speed, is you can actually increase your voltage. This is called overdriving. This is, you can't get that much out of it. You can only overvolt so much before your chip just dies. And it increases your power requirements by quite a lot, but this is something that can be done to meet setup requirements. And finally, on modern processes, you can run into variances between PMOS and NMOS. So on the manufacturing side, sometimes your PMOS transistors will be faster than your NMOS transistors. So yeah, these are all things that you need to be accounting for, and you need to be checking your design at all these different corners to make sure that it works across the board so that you get the highest possible yield, aka the highest percentage of your chips come up properly. And talking a little bit about corners. So there's, like I said, there's a lot of things that go into corners. Two that I was confused on for the longest time, so I'm going to talk about them, are PMOS versus NMOS and RC corners. So like I said, process variation can mean that PMOS and NMOS devices have different characteristics. If you see SS, FF, TT, FS, SF, these all stand for, so each of the S's stands for slow, each of the F's stand for fast, each of the T's stands for typical. And this is basically, how fast are your NMOS versus PMOS transistors in this given variation that you're testing. So you might be testing SS, slow, slow. That means that, all of your transistors are in their slowest state. FF, fast, fast. They're in their fastest state. FF is where you're going to find most of your hold time violations. SS is where you're going to find most of your setup time violations. Typical, that's just your standard. If you're not passing timing in typical, you have some problems. That means probably the majority of your devices aren't going to work when you get them back. And then there's FS, SF, fast, slow, slow, fast. One of your PMOS, NMOS devices, PMOS might be fast, NMOS might be slow, other way around. This is concerning because they are, working in opposite directions, and sometimes, that creates more issues and can unearth more issues. And then there's resistance capacitance corners. So similar idea, just, sometimes your die might have more resistance across the board just due to the chemical makeup. Sometimes it might have better capacitance, worse resistance. So that's basically what you're looking at there. Okay, so the answer, if that was all STA was, to be honest, we could just, have a script that just ran it across all corners for every design and just did it, and that was fine. You just tell it, I want to run this clock frequency, here's my design, go to town. And it could probably figure it out. Unfortunately, designs are a bit more complicated in the real world. I'm going to talk about this a bit tomorrow, hopefully, but not all paths need to meet timing. Not all paths need to get there within one cycle. Sometimes they take multiple cycles. Sometimes we don't care how long it takes for them to get there. Some signals are constant, and we don't need to time those. We also need to bear in mind, not a lot of designs have multiple clocks in them. So if you have multiple clocks, you need to define those. You need to define how you want to cross between clocks. That can raise a lot of weird concerns where you want like maximum skews between your signals or maximum delay requirements. If your design needs to communicate with the outside world, which is basically every useful design, then you need to, set margins for how long you think your signal is going to take once it gets outside of the chip, because you don't control, if you're trying to design a SPI interface, you don't control how far that wire goes once it leaves your chip. That's the board designer's problem. So you need to have margin for that and make sure you're accounting for it. I think I've covered basically everything. A lot of times there's a lot of, scripting that goes into it. With especially a lot of the more complicated cases. Yeah, that's about that. That pretty much concludes my little presentation. This advanced slide. Yeah, there's my email. I'm also in the CPES and CPES and CART discords. If you want to reach out, if you have any questions from this, obviously I'm happy to take questions now, but if you want to talk to me one-on-one, I'm always happy to chat about stuff. But with that, I think I'll open it up to questions.
Okay, I have a question. You're talking about metastability with flops. Is metastability something that you like avoid, or is metastability something that is always there that you're trying to minimize?
Realizing now I'm not sure I can hear you guys. Hang on a second. Okay, can someone say something?
Can you hear me? Can you hear me at all? Can you hear me?
I do not think I can hear you guys still. Sorry, hang on.
Yeah. Let me put my microphone. Maybe you can hear this way. 1 second. Let me turn on microphone.
There we go. Okay, now I can hear you. Sorry, that was on my end.
Yeah.
Oh. Okay.
Sorry, were you guys asking questions? Did anyone say anything during the presentation that I didn't hear?
No.
They're good.
Fantastic. All right. Do we have any questions?
Yeah, my question was, you were talking about metastability with flops. Is metastability something that you as a designer can get rid of completely, or do your flops always have metastability?
Okay, so there's two answers to that. Number one, let's say everything is on the same clock domain. Yes, you can 100% eliminate metastability. You know, as long as you're meeting the margins, you should have 0 metastability. If you have clock crossings, technically, assuming the clocks are asynchronous to each other, meaning they don't they're not phase aligned, technically, with the typical method for crossing clocks, which is synchronizers, there is always some chance of metastability, but they get the chances of that down to like 1 metastable event like in a century. So realistically, yes, you can eliminate all metastability in your design as a designer.
Yes, Henry, let me actually add a couple of things to it. So, first of all, metastability can occur in 2 cases. One, when the signal goes from the external world, so when some signal, or when signal, when you have like multiple clocks and the clock domain crossing. And in both cases, if you put the signal through 2 or 3 flops, then metastable value after some time resolve either to 1 or 0. So after 2 or 3 clocks, you will have clean signal. Now the question is whether it's 2 or 3 clocks. There is a formula which shows mean time before failure, and if you put 2 flip-flops, then in many with technologies, your mean time between failure will be like 10 years. But this is not enough for like medical devices and for like anything which isn't high risk. So then you put like 3 flip-flop, and then it goes like exponentially lower. So then in a synchronizer we use in the commercial companies, like I read journal specification, which was that time between failures is something like 10 power 14, so more than age of universe. So basically, this is what this synchronizer we have like something telephones. It's something which will be beyond like age of universe. Now, when you do clock domain question, it's actually much more interesting story. Pushing synchronizer there is not enough. The problem is that even if you put a synchronizer, you need to also avoid case where because of difference in clock frequency, you will get some information twice, or you will not get it because it will be in the middle of clock cycle, or you will violate time. Like in each case, you get like metastability. In order to counteract this, you need to use several tricks. one of the strict is that asynchronous FIFO we were talking about. But this is not the only one thing. So, this FIFO save us latencies because there are some more the things. But if you Google Cliff Cummins clock main question, you will find 3 articles that completely explains how like this can be done. So you need to read those articles before going to the job interviews because people do ask this. And this is the articles cover pretty much anything they can ask. But when you go to a company, inside company usually have synchronizer and CDC FIFO, which uses a black box. Yeah. So actually, information what the Henry presented is more than enough. So for like most of cases. Yeah. Now, second addition I would like to make. Here is a actual interview question which is asked in like different companies. So both in like GPU company and like in the aerospace company. So suppose you get chip from a foundry, and in one chip you have a setup violation, and another is a hold. But you cannot redo those chips; you have to use them. So what are you going to do to like avoid failures with those chips? So if you have the chip with a setup, so information is this presentation is enough to like answer to both questions.
You said lower the clock frequency to avoid setup, and then for
Yeah. So setup you lower clock frequency. Okay. What about hold?
he said you would have to cut out the paths that have hold timing, or you could cut out the paths that have hold timing failures. The whole phase.
No, but you see, you cannot change design. Chip is already manufactured. So what are you going to do?
Throw it away.
No, this is like insufficient answer. And if you watch presentation very carefully, it should have information that helps you to solve this question.
You think the screen has the information? The screen holds the answer?
Huh?
What's presented on the screen holds the answer, doesn't
No. It's absolutely. Okay, so.
the thing didn't very bad.
You want to add delay in your combination of.
You cannot, chip is already done. You got silicon. Like unless you use like electron microscope and precision instruments, you cannot change. And by the way, some companies sometimes do operation surgery on chips, but this is like not what the answer is. Okay, those timing, it actually depends on environmental conditions, specifically temperature. So like if you like cool this chip, like I cannot remember whether you to cool or heat it, but if you change temperature, you may change timing a little bit and get rid of this like violation. You see? Yeah, like, because like this is like a frequent question. I'm just like telling you how to answer.
You can also change it.
Huh?
You can also run it on the lower voltage side.
Low, yeah. Voltage also. This is actually a funny story like about voltage and this condition. So several years ago, I was working in a company which was doing like early AI accelerator. So they created an architecture called CGRA, or coarse grained reconfigurable array. So basically, just like with FPGAs, you have cells where you change behavior of like gates, like advice, but in CGRA you also have cells, but you reconfigure not like bit by bit, but you have the whole like white buses, dumplings. So it's like many simplified CPUs exchanging information with each other. So and when this internet hype, when this AI hype started, many companies which needed some weird custom computing devices started to repurpose it for solving AI problems. And this was one of such company, and they use CGRA. And I happened to do some debug of this chip. They were doing actually debug of like post silicon chips, and like I found that there was a bug in a processor. So one instruction, something like a third bit. One out of some number of instructions, the bit got stuck. So it put like third bit to a register one, and then it got stuck. And if you clear it, it's not unstuck. So this is like a problem in instruction, you know. And it was interesting that by changing voltage, you can make this bug actually go away. So if you like increase voltage. Yeah, so this is like environment thing you use the time. Yeah. All right.
One thing I wanted to add quickly, both questions of what happens if you get setup and hold time violations and how do you make async FIFOs were part of my interviews for Astera Labs. So do go read those articles on how asynchronous FIFOs work.
Yeah, you like essentially need to read three articles. So just Google Cliff Cummings and read them. Yeah. So, is there any questions about like timing and stuff? Yes. So tomorrow we will continue. One thing I have that actually in addition to installing Wilken on your system, you can also try to boot from a bootable SSD. So I have a bunch of bootable SSD. The only thing that I didn't check all of them. So actually, if some of you can try to boot it on your system right now, if it works, we can do it in this way. So can somebody try to boot these things on your computer? You just need to like insert it if you know how to boot it. So does anybody want to try or not?
Dude, my computer's bad.
Okay. Yes, anyway, let's just install in this case Wilken. Yeah, but if somebody has installation problem, we can try to put a bootable SSD.
Yeah, I can try one of them.
Okay. It's yours.
That's okay, I just wanted to make sure. I want.
I put it somewhere.
Oh, no, it's okay, as long as you have it.
No, I need to find the back otherwise I should have.
What's the next on this?
Let's see. So.
Should be Wilken home.
Good.
Yeah, okay.
You want like boot as?
That's how you do it, Simon.
Do you want boot,
yeah.
boot as it?
So in Windows, let me show how to do it. Where's my eyeglasses? Okay, so this is how to boot from these things like in Windows.
So you go to settings, and you go to setting called startup, I think, like advanced, change advanced startup options. So disk is here. So you go to like advanced startup and you press restart now.